So as folks join back in, I talked to one group about this, but if you got to question 6, I might have given it away in the Google Doc. Oops. But did anyone have an idea of which galaxy was a model and why we would know it's a model even if I didn't label it as a model?
The Milky Way.
Yeah. How did you know, Maddie?
Well, it was because like 2 classes ago, or like last class, you were like, you can't actually take a photo of the Milky Way because we're too close in.
Yeah, we're in it. We're inside that galaxy. We can't take a picture. So perfect. Thank you. Yeah, that was my little extra question. Every other picture, no matter how weird it looked, was a galaxy. So even this one down here, NGC 520, that was when I talked with one group, is probably galaxies colliding. So you can see maybe there's multiple disks here that are merging to become one bigger galaxy, just like the Milky Way and Andromeda will do eventually. IRAS, lots of numbers. I think it's also the Bird Galaxy is also probably 2 disk galaxies colliding, as is M82 might also be some form of merger that happened where maybe it's not a disk galaxy but an elliptical merging with a spiral. So we can see that there's they look really crazy, but those are real images. Just whether or not they're visual light images is, I think this is not visible light, but the rest I think mostly are. Other main thing that I was hoping you would pull out, which I think a lot of you were getting this from what I was talking to, is that there's galaxies that look kind of boring and don't have much structure, and then there are galaxies with lots of pretty structures, so where we can see arms. And so the main thing is that we're breaking them up into those 2 categories, which astronomers call spirals and ellipticals. And I also got a question about this, where if you're classifying the Milky Way, what did people think? If you put in the chat, what did you think the Milky Way, what type of galaxy was the Milky Way? Throw it in the chat. So definitely a spiral. We do think the Milky Way has a bar. So this thing here, it's not the best model, but the Milky Way we do think has a bar. So this is kind of the bar of the Milky Way. So we think it's an SB galaxy. Mostly it gets classified as an SBC, so S capital B C galaxy, lowercase c, because it has quite a bit of structure in those spiral arms, and there's quite a few of them. But that's slightly difficult to tell, again, because we are inside of it. And this is just based on observations we have made of how the stars are moving around our galaxy. Sweet. So what you all just did was kind of build your own version of the Hubble tuning fork, which is called a tuning fork because it kind of looks like a tuning fork. And in the Hubble tuning fork, we have our elliptical galaxies. Lower numbers means more round, higher number means flatter. And then our spirals, we divide into barred spirals and unbarred spirals. And then we look at how tightly wound the arms are, how structured are the arms, to figure out what class it is. And I mentioned this with one group, whether you're an A, B, or C, is really kind of a fuzzy definition. So even astronomers will classify the same spirals with different A, B, or C labels. So I am not ever going to grade you on whether or not you can distinguish between a type A and a type B spiral. That is never going to be something I do. I might ask you if it's a barred spiral or just a spiral, but I will not expect you to be able to tell the difference between a B and a C. I think that's silly and I can't do it either. So don't worry about that. Then we have our irregulars down here, which don't quite fit on the tuning fork, but are an important class of very cool galaxies that just look weird. And some of them are mergers. Cool. So now I'm going to talk for the rest of class, just get a little bit more detailed on the different types of galaxies and how they are different, what astronomers have noticed about the differences between spirals, ellipticals, and irregulars. So with spirals and barred spirals, we notice they have a lot of gas and dust. A lot of gas means there's a lot of stuff to form stars out of. So there's a lot of star formation happening in spirals, which is why we can see the spirals have all these pretty colors. So spirals have blue light from O and B stars. The red light is mostly coming from hydrogen gas. That's that H alpha emission we've run into quite a bit. So the hydrogen gas emits red light, so we can see red in these spirals from the hydrogen gas. Because there's this kind of organized motion, the gas will mix and collide, causing new stars to form. Spirals kind of have a range of sizes from about 20,000 light years across to 100,000 light years across. So we can't necessarily assume all spirals are the same size, which sucks because if we could figure out how far away they are, but we can't. Spirals are also occasionally called blue and new galaxies. So I talked to one group about using color to classify galaxies. This is a way spirals are usually bluer. So astronomers will also use color to define what different galaxy types are. We'll say spirals are more blue, and then ellipticals will be red. So they're bluer because there are O and B stars, and they are newer because there are new stars in them. So they're not necessarily younger galaxies. The stars in the galaxies, though, are younger. So probably all formed around the same time, but spirals have continued to form stars over time. So we still see star formation. We still see those stars that don't live very long. So we see all this blue light. The centers usually look more yellow because there's often more old stars in the center. So we're more dominated by F and G type stars when we get to the center of galaxies. All galaxies will still have a supermassive black hole, not just the Milky Way. So that's something that we see both in spirals and ellipticals. When we classify spirals, there are two big classes. So there's barred spirals and unbarred spirals. About 2/3 of the galaxies, 2/3 of the spiral galaxies where we can actually see their structure, we see bars. So bars are pretty common. We can also classify a bit by using the size of the central bulge, the size of the nucleus, and then how tightly wound the arms are, with A type having more loosely wound arms, and then C type having the really tightly wound arms. So NGC 6902 over here might be a C spiral. Sometimes you also add in whether or not there's a ring. So these galaxies in this left column have rings where we can see there's a ring around the nucleus. So you can have both a bar and a ring, like IC 5240 down here, which has both a ring and a bar. So does NGC 1433. Just a little note, when I say all these names, NGC means New General Catalog. So it's just a catalog of galaxies. Sometimes you're named after what observed you. So ESO is the European Space Observatory. So you can get a number based on what telescope observed you, or you can get a number based on a catalog that you are in. So a lot of them are M, which is the Messier catalog, or you'll see NGC a lot. Some galaxies also have names that are more fun, like Whirlpool or Firework or something. But when astronomers talk about galaxies, they often use this NGC number. Another way we can think about galaxies, about spirals, is that they will not always be, these are all face-on spirals where we're seeing their structure. Not all spirals will be face-on. Some of them will be edge-on, where we're seeing the edge of the disk. We can still get an idea it's a spiral based on how the stars are moving and what color it is. So if there's still a lot of blue light, this is probably a spiral galaxy, not just a really flat elliptical. And if there's organized rotation. So all spirals have this nice organized rotation, which we can measure in these edge-on galaxies. So this is still a spiral, but you can't really tell if there's a bar or how many arms there are. So we can say this is a spiral, but you can't classify it further than that. But there's still a lot of, we will dig more into this. And if you do the Galaxies lab, you will use an edge-on spiral to measure all kinds of cool things about that galaxy that we couldn't do if we were looking at a face-on spiral. So face-on, edge-on, both spirals, we can learn really different things by looking at different types of galaxies, different spirals, different orientations of spirals. Any questions on spirals and how we classify them? So the other big classification in Hubble's scheme were those elliptical galaxies. These are the ones that I think are kind of boring, but that's partially because I study star formation in galaxies, and ellipticals don't really have any star formation happening. So they don't have the nice spiral structure. There's pretty much no organized motion. So the stars in the elliptical galaxies aren't rotating around a center. They're all kind of moving in different, so they are orbiting a center, but they're all going in different ways. There's no organized rotational motion. All the stars are just doing their own kind of orbits in whatever direction they want. So they look much more messy when we think about velocity structure. There's no spiral arms. There's not very much gas and dust. If you don't have any gas, you can't form new stars. So there's no new stars forming either. So sometimes these are also called red and dead galaxies. So they are redder because there are no blue stars. So there's no blue light. There's no O and B stars. So there's not very much blue light, which makes them redder. And then they're dead because they're not forming new stars. So again, blue and new, red and dead. We think of spirals versus ellipticals. Yes. We can further classify ellipticals based on how spherical they look. So an E0 elliptical galaxy will be a pretty spherical elliptical, whereas we can go up to E7, which is going to be something that looks almost like a disk, but doesn't have that blue light, doesn't have any organized rotation. The other thing to think about is that, again, the classification of an elliptical might depend on the orientation that we see it. So it's very possible that if this E0, if we tipped it, it would start to look like an E7. We can't tell, we can't travel around these galaxies. Whether or not they're perfect spheres or kind of more oblong football shapes, we don't really know, because we can't travel around. We have a two-dimensional view of this galaxy. But we can classify that two-dimensional view as best we can using this elliptical measurement, this 0 to 7 number. Sometimes you will also see a plus. The plus just means there's an extended disk. So you can kind of see, especially in this E4 over here, there might be kind of some fuzziness extended off, where could be a sign that dynamically something weird happened to it, like this had tidal forces or something. We don't 100% know, but understanding why we see these different ellipticals and spirals is a big question that extragalactic astronomers are trying to answer. Most ellipticals we see are very, very big. So elliptical galaxies, the biggest galaxies we see are all elliptical galaxies. So the most massive, the largest in radius are all ellipticals. But we do get kind of a range in sizes. So we'll also see dwarf elliptical galaxies, so very, very small galaxies that also have little to no gas or dust. They're often satellites of larger galaxies. So like the moon is a satellite of Earth, you can have a dwarf galaxy be a satellite of like Andromeda, a dwarf elliptical. So that just means they're gravitationally bound to a larger galaxy. The Milky Way used to have a dwarf elliptical satellite galaxy, but it ate it. So through galactic cannibalism, Milky Way ate the Sagittarius dwarf galaxy, and it has become part of just the Milky Way. Another thing that's kind of fun to think about, and if anyone has an idea in these last few minutes, what might be a defining feature of a galaxy versus a globular cluster? So a globular cluster is a spherical group of stars. A dwarf elliptical is a spherical group of stars. What's the difference? Why are these two things? How might we draw a line between a galaxy and a globular cluster? Any ideas if anyone wants to throw it in the chat or unmute themselves and yell out? So basically maybe black hole at the center, that's very important. Most galaxies will have supermassive black holes, so that is one way, so that's perfect. There are a few galaxies we've seen that don't have supermassive black holes, so there are a few dwarf galaxies that don't seem to have supermassive black holes at the center. There's something else galaxies tend to have that globular clusters don't, that I've mentioned a little bit today. Not seeing it yet, so I'm just gonna really quickly, and that's gonna be dark matter. So every galaxy has dark matter. Again, there are a few that don't follow this. There are a few galaxies we've seen that don't seem to have dark matter, but most galaxies have dark matter. Globular clusters exist inside of the halo of another galaxy, so a dark matter halo of another galaxy, but they don't have their own dark matter halo. Dwarf elliptical galaxies will have their own dark matter halos. So they have supermassive black holes in the center, they have dark matter halos. Another thing that's slightly fuzzy is that galaxies, globular clusters will have stars that are all the same age, which is how we use the HR diagram to find their ages, whereas galaxies will have different populations of stars. So not all of the stars in a dwarf galaxy will be the same age, whereas all of the stars in a globular cluster we think are pretty much the same age. So those are kind of the three things: supermassive black holes in the center, dark matter halos, and then just different populations of stars are how we draw these lines. Dwarf elliptical galaxies do tend to be also slightly larger than globular clusters. They tend to have masses of 10 to the 8 solar masses. So the Milky Way was 10 to the 11. These dwarf galaxies get down to 10 to the 8. So anything that's a dwarf galaxy is usually, we kind of draw the line at 10 to the 9 solar masses or less. But most of them seem to be around 10 to the 8. So just to finish this off, since we have 2 minutes left, very quickly, the last class is then irregular galaxies, which are galaxies that don't fit either spirals or ellipticals. Often they look like either merging galaxies, like this one here, that has lost its structure because it's in the process of becoming a new structure, or they're very, very small, so small they don't form any nice organized structure, like this galaxy down here, which is the Large Magellanic Cloud. So this is one of the Milky Way's satellite galaxies. It has two, the Large and Small Magellanic Clouds. We cannot see them in the northern hemisphere, but if you do go to the southern hemisphere and you are somewhere dark and you look up at night and you see some smudges on the sky, those are the Large and Small Magellanic Clouds. So they're just so small, they don't necessarily have structure. So that's kind of the two ways that you can get irregular galaxies. You can slam two galaxies together, causing them to lose structure, or you can just have a galaxy so small that it never really develops structure. And that is kind of our big classification system. So we have spirals that we split into barred and non-barred. We have ellipticals, which we classify based on how round they are. And then we have irregulars that don't fit into either of those classes. So with that, I think we will wrap for today, unless anyone has any questions in the last 30 seconds or so. I'm not doing anything. So next class, we will finish up talking about galaxies and start putting those into our picture of the entire universe. Have a lovely